Today we're going to discuss the area between two curves or between two functions in terms of x. We found that we could calculate areas of regions that lie under the graph of a function, but under the graph of one function to the x-axis. Here, we're going to use definite integrals to find the areas of regions that lie between the graphs of two functions, like we have in the do now. So let's take a look. We have functions f and g that are continuous on a closed interval a, b. The graph of f is in red and the graph of g is in blue. And f is above g, so that's why we write f is greater than or equal to g for all x on ab. To find the area between these two curves on the interval from ab, well, it's the region bounded by the functions themselves and the two vertical lines at x equals a and x equals b. So the area of the region between the two curves, which I called region A, is here. And the question is, how can we use definite integrals to help us get the area of region A? Well, let's just review what a definite integral represents. Well, if we take the graphs of these functions separately and we separate them, the graph of f and the graph of g, the definite integral of f, okay, so let's write this down. So the definite integral of f of x with respect to x from a to b would represent the area from the graph of f in between the two vertical lines x equals a and x equals b to the x-axis. So that definite integral is the net area under the curve. And the definite integral from a to b of g of x dx would represent the net area from the graph of g bounded by the two vertical lines x equals a and x equals b and the x-axis. So it would be this region. So now the question is, how can we use these two answers to get the area that's above the x-axis between f and g? Well, it seems that if we combine these two, we can get the area of the yellow region by subtracting these two areas. We take the red area under f and subtract the blue area under g. So it's the difference of these two integrals, which by properties of definite integrals would be the definite integral from a to b of f of x minus g of x with respect to x. Let's look at it another way. So if we use vertical rectangles to approximate the area under the graph of f, the definite integral from a to b, we would take a vertical rectangle and we see that the graph and with a width of delta x, which is really tiny, we see that we could represent the area of the kth rectangle Now, we would like to have a rectangle inside the region in question. So the area of the kth rectangle under f is the height, which is whatever x is, f of x sub k, times the delta x. Okay, now in the same interval, delta x, the height of the rectangle that we put in the region under G can be represented as G of x sub k, and we multiply it by the tiny width. So the area, and I'll do this in yellow because I had it in yellow, the area of the kth rectangle between f and g. Okay, so we're talking about this rectangle. at the same x sub k? Well, we would take f of x sub k and subtract g of x sub k and multiply it by the delta x. So that would be f of x sub k minus g of x sub k, and this would be the height of that rectangle times delta x. And then, of course, if we sum up infinitely many of these rectangles, we could represent the area of the yellow region as follows. So the area is equal to, now the sum from k equals 1 to n of f of x sub k minus g of x sub k times delta x. So we partition the region into n subintervals of equal width of delta x. And if we want to sum up infinitely many rectangles, we put the limit in front. And this, lo and behold, is a Riemann sum. And we could represent this Riemann sum, or the limit of this Riemann sum, as the definite integral from a to b of f of x with respect to x. Oh, well, actually, we could write f of x minus g of x in brackets, and the delta x morphs into a dx. So this is consistent with our do now. We take the area under f and subtract the area under g. And by properties of definite integrals, we can combine them into one definite integral. Remember, this is the height of the rectangle in between the graphs of f and g. Right? And the dx is our delta x, which is the width of the rectangle. All right, so let's consider one other idea that's important in this topic. Suppose we change the position of f and g with respect to the x-axis. We saw previously that if the graph of the function is below the x-axis of a single function, then the definite integral would represent net area, and it could be negative. But what happens if we shift the region between two curves in another quadrant with respect to x, like as follows? Suppose I take the region f and g and move it down a little. Like I have in this diagram, I moved it down a little bit. Well, let's see. If we take the region between f and g in the diagram above and cut it out, I could shift that anywhere on the plane. So when we translate a region, the area remains unchanged. And if we take a look at our representative rectangle, the definite integral from a to b under f to the x-axis would be this region. The definite integral under the graph of g to the x-axis would be this region. Oh, I should put that in blue. This rectangle here. So when we perform the operation f minus g, notice that this is already negative because that piece of the curve is below the x-axis for g. And this is positive. So if I take this positive quantity and subtract this negative quantity, which is what the region, what the integral tells us to do, we would still end up with a positive answer for the height of the representative rectangle. So it turns out that when we deal with the area between two curves, we should write down in our notes that the area between two curves is unchanged by translation. So here, the formula doesn't change. The area between the two curves depends only on the continuity of f and g and the fact that one is above the other, not on their position with respect to the x-axis. The area between these two curves in the second diagram is still the same integral. And we have to remember that the height of the representative rectangle is always the top curve minus the bottom curve. Okay, so let's summarize that on the next page. The area between two curves, or functions, I should say. We mean functions here. F and G are continuous functions for x on the closed interval AB. And again, F has to be, well, one sketch has to be above the other, and we won't be able to tell which is above the other unless we sketch. So here is a part of the course where we must sketch. Then the area between F and G and on this closed interval of x from a to b is represented by the definite integral from a to b of the top function minus the bottom function, all in one integral with respect to x. And remember, this represents the height of the kth rectangle in our Riemann sum. And when we have that definite integral, we're taking the limit of this Riemann sum as the number of rectangles increase without bound. Okay, now we have to make sure that the top and bottom functions in the entire interval are the same, because we'll encounter problems where they change. And if this happens, otherwise, we break the definite integral, into the sum of two integrals, into the sum of two definite integrals. And we'll see that in a little bit. So let's take a look at a problem. And remember, the most important thing here is that after we sketch, we have to identify the top function, the bottom function, and subtract. And these are in terms of x. Now let's take a look at this problem. Find the area of the region bounded by y equals x squared plus 2, y equals the opposite of x equals 0, and x equals 1. So the first thing we must do is sketch the region. There is no other way. We must have a picture. So let's sketch it quickly. And these functions are pretty easy to sketch. They don't have to be accurate. So y equals x squared plus 2 is a parabola whose vertex would have been at the origin, but it's shifted up 2 units. So I'll just put this. Okay, so we got a parabola there. It's not really that perfect, but let me just try to perfect it a little bit. I exaggerated the parabola. So, okay, so this is, and we should label it y equals x squared plus 2. Y equals negative x is a diagonal line through the origin with negative slope. So it looks something like this. And again, it's not perfect. And now we have to consider the two vertical lines. So we're looking at the two vertical lines at x equals 0, which is it's the y-axis, and x equals 1, which is 1 unit over. And remember, these are always vertical lines. So what is the region between all of these, or bounded by everything? Well, the region would be this piece, right? This is the region bounded by or between the parabola, the line, and the two vertical lines. So we set up our integral. But before we do that, we imagine a rectangle in the region. So let's see, did I run out of colors here? I did. Okay, so we imagine this rectangle in the region, and we draw this little vertical rectangle. And we have to make sure that the top of this rectangle and the bottom of this rectangle, like a rubber band, as we stretch it through the region, does the top always hit the red curve and the bottom always hit the blue curve? It looks like it. I mean, even if when I get here, the top always hits the red curve and the bottom the blue curve. So the vertical rectangle is consistent with the curves, top and bottom. So the integral would be the definite integral from x equals 0 to x equals 1, because we're summing up the areas of all the rectangles between those two vertical lines. And what are the heights of the rectangle? Top, which is x squared plus 2, minus the bottom, which is minus negative x. So this expression represents the height of any rectangle in the region, in the kth interval, with respect to x. And the rest is just the first fundamental theorem of calculus. So let's integrate this. So the first thing we should do is use algebra and combine. So we get x squared plus x plus 2. And don't forget to use your parentheses. And this is pretty easy to integrate. It's the power rule. So we add 1 to the exponent and divide by that exponent. X squared over 2 and 2x. And now we use the first fundamental theorem of calculus. And don't forget, with the first fundamental theorem of calculus, we substitute the upper limit first and then the lower. So this would be 1 cubed over 3 plus 1 squared over 2 plus 2 times 1. And again, put this in parentheses because this is the antiderivative at the upper limit minus the antiderivative at the lower limit. And you could see that that one's going to come out to be 0, but I'm going to substitute the 0 in for x to emphasize the first fundamental theorem of calculus. And we have 1/3 plus 1/2 plus 2 minus 0. And when we combine like terms, well, we have to put everything over 6 here. So if we do all right, this one is asking us to get the area between the curves y equals x squared minus 2 and y equals the opposite of x plus 4. Now, again, they didn't give us any x values. We'll see why in a minute. Because when we sketch these two, and let's just quickly sketch them. All right, the first curve is a parabola shifted down 2 units from the origin. Just like the other one was shifted up 2, this is shifted down 2. So again, I just need a rough sketch. So I'll make my parabola look like this. Okay, and this is y equals x squared minus 2. And then the other curve is a line with a y-intercept at 4. So I'm going to put down, it's in slope-intercept form. So 1, 2, 3, 4. So the y-intercept is there. And the slope is -1. So again, because this is a rough sketch, I'm just going to draw a line with a negative slope. And again, we could pick more points, but it's really not necessary. Because the important part here is to know which one's on top and which one's on bottom. Now, the reason why we don't have x values is because the region that we're interested in, bounded between these two curves, those x values would be at the intersection points, right? And that would be the x value at this intersection point and the x value at this intersection point. So the intersection point, the x equals, could be a boundary of the region, but it could also be an intersection point. So the first thing we have to do here is find the intersection points. We don't know what our limits of integration would be. And to get those intersection points algebraically, we set the two curves equal to each other and solve. And these should be pretty easy to do. We get this into standard form, and we get x squared. Oh, wait, I miscopied something. This should be a 2. So it's x squared minus 2 equals this. I add the x and I subtract the 4 and I get this quadratic, and we factor to x plus 3 times x minus 2. And we get that x plus 3 is 0, or x minus 2 is 0. So that means the intersection points are at x equals -3 and x equals 2, which looks about right. This looks like x equals -3, and this looks like x equals 2. We should also get the y values, but they're not necessary here. But yeah, we really don't need them. Now, again, we use a vertical rectangle, and we think of this vertical rectangle as a rubber band. The top is the blue, the bottom is the red, and as I move this vertical rectangle through the region, I see that the top will always hit the blue and the bottom will always hit the red. So the definite integral that would give us the area of the yellow region would be from x equals -3 to 2. And remember, we always accumulate area from left to right. The top function is the line, the opposite of x plus 4. The bottom function is the red, which is the parabola, x squared minus 2. And be very, very careful of the order that we put these in. So the top here happens to be the line, which is in blue. This is the top. And the bottom is the red. Okay, now pause the video and calculate the area between these two curves, and we'll check in a minute together. So combining like terms, we get the opposite of x squared minus x plus 6. We anti-differentiate. Be careful here. Okay, and then we substitute the 2 first. Notice I substituted the 2, and then the -3. And whenever we substitute a negative number using the limits of integration, we always should put that in parentheses, as I have here. Okay, because we've got a lot of negatives here. So be very, very careful with the symbol. Now, this does not mean -2 cubed. It means the opposite of 2 cubed. You could think of this as a -1 times x cubed over 3. And there are many mistakes that could occur here, but going through all the arithmetic, the final answer should be 20 and 5/6. Okay. All right. And that took a while, but we did it. So that takes care of the area between two curves. And again, we see two scenarios. And when we integrate with respect to x, we use a vertical rectangle, and the formula is top minus bottom. And sometimes we have to solve for the limits of integration. Okay, I hope that this clarifies any question. And I wish you all a wonderful day. Bye.